Welcome friends to my YouTube channel Sommo Physics. On previous lecture, I will discuss about the equation of motion of a particle in a central force field. And from this, I derive that total energy of a particle in a central force field remains constant. Okay. Now today, I shall discuss about the Kepler laws of planetary motion. What are the various laws that we know, that you already know? Now let's proceed. So Kepler's first law states that each planet revolves around the sun in an elliptical orbit. Okay. Each planet revolves round the sun in an elliptical orbit with the sun at one of its foci. Okay, that means if there is a elliptical orbit, say this is the major axis and this is the minor axis, then suppose the sun is at one of its foci, this is here. So if the planet is located at this position, say, then it is obviously r theta. Okay, say this is r and this is theta. So this is the picture. So this is the position of the sun that is located at one of the foci of the elliptical orbit, and this is the planet. Okay, so each planet revolves around the sun in an elliptical orbit with the sun at one of its foci. This is the first law. The second law is that simply we all know that aerial velocity of the radius vector is constant. Aerial velocity of the radius vector is constant. What is it? That means aerial velocity means the area swept out per unit time. This is constant. Or simply you can say the line joining the sun to any planet traces out equal area in equal time interval. Okay, the line joining the sun to any planet traces out equal area in equal time interval. That means the aerial velocity, area swept out per unit time, this is constant. So this represents the second law. Okay, so how we can prove it? So let's proceed. Suppose at initially a planet of mass m is located at that point, say P point. Now after a small time interval, say dt, the planet rotates an angle d theta and moves to the position q. Okay, so this is simply r, and since d theta is very small, this is also r, and this is r d theta. Okay, now suppose initially the planet located at P. Now after a small time dt, it rotates an angle d theta and occupies the position q. Okay, so since the d theta is small, this line is also r, and what is pq? Pq is nothing but r d theta. Now what will be the area swept out by the planet in time dt? If the area is dA, then we can write it half into, this is simply r into that height r d theta. So this is half r square d theta. Okay, now what is dA dt? dA dt will be half r square d theta dt. Okay, now we all know that angular momentum can be written as m r square d theta dt. From this we can write r square d theta dt, this is equal to L by m, and this is constant. So what we can write? We can write L by 2m. L angular momentum is constant and m mass of the planet, this is also constant, so aerial velocity remains constant. Okay, so this is how we can prove the Kepler's second law. Now next we discuss about the third law. What is it? We all know the third law is what? Third law is the square of the time period of revolution of a planet round the sun is proportional to the cube of the semi-major axis of the elliptical orbit. That means t square simply proportional to a cube. Okay, the square of the time period of revolution of a planet round the sun is proportional to the cube of the semi-major axis of the elliptical orbit. And how we can prove it? So let's proceed. Now we know if capital T represents the time period of revolution of a planet round the sun, then area of the elliptical orbit can be written as integration over dA, and that can be written as dA dt into dt. So limit will be 0 to capital T, where capital T is the time period of revolution of the planet round the sun. From above we can write as dA dt as L by 2m. So this is into dt. So this is simply LT by 2m. Okay, now we can find the area of an ellipse in another way. We know from mathematics that the area of an ellipse is pi AB. Okay, A is the semi-major axis and B is the semi-minor axis. Now in case of a ellipse, we all know eccentricity is what? Square root 1 minus b square by a square. And from this b can be written as a into root over 1 minus epsilon square. So what we get? Pi a square root over 1 minus epsilon square. Okay, now again simplifying, what we get? Pi a square into root over 1 minus epsilon square. Now from conic section equation we can easily write epsilon square, this is equal to 1 plus 2el square by mk square. Okay, this we can write from conic section equation. In next class we will prove the conic section equation and this relation. So if we substitute this value, what we get? Pi a square into 1 minus 1 minus 2el square by mk square. 1 cancels, so what we get? Pi a square into root over minus 2el square by mk square. Now in the next class we will also prove it that the total energy of the orbit depends upon the major axis, and which we can write as minus k by 2a. That means here we put minus k by 2a instead of e. In the next class we will discuss it and prove it that e equal to minus k by 2a. So what we get? we get pi into a to the power 3 by 2 square root L square by mk. Okay, now if we equate the two values of a, then we get LT by 2m. This is equal to pi into a to the power 3 by 2 square root of L square by mk. Now squaring both sides, what we get? L square t square by 4m square. This is equal to pi square a cube L square by mk. So L square cancels, from which we get t square equal to 4 pi square m by k into a cube. This term is constant, so we get t square is proportional to a cube. This is Kepler's third law. Okay. So in my next video I will discuss about the conic section equation and also discuss about the expression of total energy, that is E equal to minus k by 2a. That is, we will prove it in our next class. Okay, thank you.